Welcome everyone to the final section that we teach here in Math 124. This is section 3 of chapter 7, averages and moving averages. And like it says here, right, we're going to be talking about more than just like your kind of standard averages, right? We're going to actually be doing averages over infinite sets. And the claim is this will be one of the applications of the integral, right? This is chapter 7, further applications of the integral. So, before we get to that complicated bit, though, let's actually go back and review how to take kind of the average over a finite set. So here we have a nice set of numbers. We have some y1, some y2, all the way up to, you can have as many values as you want, so n values I'm going to say. And then, right, the average value, or sometimes this is referred to as the mean, or the mean value, of the set is denoted by this y with a little bar over it. Right, so this is the average or the mean. And it's given by that this y bar is equal to, and right, when you normally take these averages, you sum up all the values, y1, y2, all the way up to your last value, and then you divide by the number of values that you have. So in this case we have n values, so you just divide by n. So this is a little bit complicated, right? Because, I mean, we have to keep it kind of arbitrary. We don't know how many values we have n. We don't know what they are, so you get all these weird subscripts and stuff. But when you come to actually do an actual problem, right, I think it makes sense. So here is a set, and I want to figure out the mean, right, or the average of the set. So I'm going to add up all the values together, 1 plus 4 plus 9 plus 16 plus 25. And then I'm going to divide by some number, right? And altogether there are 1, 2, 3, 4, 5 numbers that I added together, right? So however many numbers you added together, 1, 2, all the way up to n, right? You divide by that n. So that's why I'm dividing by 5 here. And so, okay, let me get out my calculator just so that I don't make any silly mistakes. All right, and we have 1 plus 4 plus 9 plus 16 plus 25. Enter. That is 55. And when I divide that by 5, we're going to get 11. So 11 is the mean of the set. It's the average value. Okay. So this is kind of your standard averages over finite sets. But we're going to be trying to tackle problems more like this example 3.3. So guess the average height of this function, which is x squared minus 4x plus 5, on a specified interval, so between x equals 1 and x equals 4. So you can see it takes quite a bit of heights on, right? Infinitely many heights, in fact. We have 2 here, it goes down. I think that this minimum point right here is like 1, and then it goes back all the way up to 5. And so, okay, guess an average height. What is the average height? Well, okay, it was 2, and then it was 1, it goes back up to 2, it goes up to 5. So I don't know, I would say maybe an average height would be somewhere around like 3 or something like this. So average height is equal to 3 question mark, right? This is our guess. We think, yeah, it seems reasonable, right? It kind of would be silly to take, say that the average was any less than 1 or any bigger than 5. But yeah, somewhere in the middle between 2 and 5, right? Halfway in between these 2 and 5, I mean, it would be like 3.5 or something like this, but you can see it seems to take on more smaller values than bigger values. So that's why I guessed 3. Again, this is just a guess, but the claim is we can use calculus to figure out the answer to this. So we have defined here the average or the mean of a function, right? And really this means the height of the function, the y values of the function, on the interval from a to b. So in our case up above here it was 1 to 4. And just as before, we're going to denote this as f with a little bar over it. And it is given by, so this average is equal to, and so you're going to have this integral from a to b of f of x dx. And then out here, so this would just be the area under the curve. Here you're going to divide by the length of the interval so 1 divided by b minus a. And this will give you the average height. So using this, I want to go back and actually check my answer, right? So 3.5, go back and actually calculate the average in this example above. Okay? So here we have f bar, the average height, is equal to 1 over b minus a. So those b's and a's, they come from the interval. So here's my interval 1 to 4. So I have a, the start of that, b is the end. So this is going to be 4 minus 1. So like I said, this is the length of the interval here. 4 minus 1 would be length 3. So this has length 1, 2, 3. Okay, so that's the length of the interval, and now I'm doing the integral here from a to b, so in this case it's 1 to 4, of my function. So x squared minus 4x plus 5 dx. So that's going to be 1/3. And now in order to calculate this out, I'm going to need to figure out an antiderivative, right? I'm going to use the fundamental theorem of calculus here to calculate out this integral. So, okay, my capital F would be equal to, so capital F of x. So something when I take the derivative, I get x squared. That's going to be like 1/3 x cubed. Something when I take the derivative, I'm going to get negative 4x. So again, this is again like guess and check almost. So if I take the derivative of this, the 2 would come down. That would give me negative 4x to the first power. Okay, good. And then plus 5x. Okay, so there is my antiderivative, or my definite integral, right? I guess I would need a plus c for that. So according to the fundamental theorem of calculus, this is going to be f of 4 minus f of 1. So multiply everything by 1/3. Notice the 1/3 is out here and it gets multiplied by everything. So that's why I have those parentheses. So f of 4, okay, let me get out my calculator here so I don't make any silly mistakes. And to do these kind of quickly, I'm going to go ahead and just graph it since I have a couple values to plug in. So let's see, 1 divided by 3 times x raised to the 3rd power minus 2x raised to the 2nd power plus 5x. And I'm going to go to my table. Let me make sure that I have it set on reasonable values though. Starting at 0, jumps of 1. Okay, good. So I need f of 4, 9.333, and f of 1, so up here we can see, 3.333. So 9.333 minus 3.333. So this is going to be 6 divided by 3, so that's going to be actually 2. So in this case, the actual average value was 2, right? So I guessed it wrong, right? I guessed it was 3, it's actually 2. But now we know. Okay, so this is how we can actually use this definition to calculate out an average height of a function, which again, this function took on infinitely many values, here from 2 all the way down to 1, right, and all the numbers in between, infinitely many numbers there, and then all the way up to 5. Okay, let's move on. Alright, so the next topic, the final topic, is this thing called a moving average, right? It was in our title. So when a function, the claim is, has a high volatility, right? So it's moving back and forth a lot. You can kind of think like stock prices or something like this. They move up and down a lot, or really a lot of real-world examples do. It may be reasonable to look at actually a moving average. So the n-unit moving average, so you have to specify how many units long it is. So n-unit moving average of a function f ending at x, we'll see what I mean by this here in a minute, is denoted by, so f bar, but now it depends on x here, right? So this is going to be f bar x. And is given by, and we have, so f bar x is equal to, and we're going to have the length, so this is going to be, it's an n unit, so 1 over n. And then the integral, and this is where it gets a little bit strange here. We need to change up our variable here. So let's see, I'm going to use the variable t. So f of t dt. And we're going to be integrating over an interval, like I said, of length n ending at x. So we're ending at x up here. So if the length of the interval was n, it needs to start down here at x minus n. Okay. So this is our definition, and I find that this is a pretty confusing definition, right? And so in order to kind of see what this actually means, what this is doing, I'd like to play a little bit with a moving average on this Desmos calculator thing, so I actually have it all brought up for us. Here it is. And so I have, right, any old function. So on the left-hand side here, any old functions, mildly complicated. And, right, you can see that there's quite a bit of volatility, right? It's wiggling back and forth quite a bit, and it looks like kind of a difficult function, right? And then I have an n-unit moving average. So you can kind of see the length at the interval here right now is supposedly 5. And I can shrink that down. So now that the length of this interval is actually like 3. So actually maybe let me zoom in a little bit so you can really see. And I'll specify this here at maybe negative, 10. That's what I was going for. So this is where it's ending. So at negative 10. So you can see it's length 3, ending at negative 10. If I increase this, it would be negative 4, negative 5. Sorry, 4, 5, right? So this is the length of the interval that I'm considering. Okay, ending at, in this case, negative 10. So if you were to do that integral, so 1 over n, in this case I'm specifying my x value, right? My x value is negative 10 right now. So I'm doing the integral from this negative 10 minus 5 to negative 10, so that's why it's going from negative 15 to negative 10, of this function, right? And if I was to integrate this, it's saying that the average height of the function over this interval is 6.75. And so this line right here is at height 6.75. 6.75 and change. And this point right here is that average value, again, ending at x, right? So that's why it's at the right-hand endpoint. And so something nice that happens with this Desmos calculator is, right, I can hit this play button. So I'm going to change my x value. So right now it's negative 10. I'm going to hit play. And so this is the 5-unit moving average of our function. And you can see that this green point is moving up and down and tracing out kind of a new function, right? And so actually, if I am to click this button right here, you can see this is the function it's tracing out. So you can see this one looks a lot smoother, right? The moving average is a lot smoother of a function. So when stocks or something like this move up and down quite a bit, if you take an average over the past few days or so, you can kind of start to see a pattern emerging. So, right, this is kind of the underlying pattern here. And you can see what happens. So let me pause this for a second. If I decrease the amount of days, right, the number of units, I would say, the number of units, you can see that you start to get more wiggles. So with a 2-unit moving average, there's more volatility, right? But it's a little bit closer to the function, this blue function, right? And as I increase the number of units, you can see it really starts to take on this parabola-looking form. There's very little variation, right? And you really get to see what the underlying kind of structure of this graph is. So you can start to determine patterns and things like this. So this is what the moving average really looks like, right? This is what the moving average is doing. And so we would like to use this idea here and actually be able to calculate out a few of these. So that's going to be our final task. Let's go back and try it out. All right, so I have this function 1 plus root x. I would like to calculate out the 3-unit moving average for this function f of x. So my n value is going to be 3. Let's go ahead and write down the definition here. I think I'm going to need a decent amount of room, so I'm going to start over here. F bar of x is going to be equal to 1 over 3. And then this is going to be the integral from x minus 3 to x. And now I need f of t dt. So instead of f of x, everywhere I see an x, I'm going to put a t. So this is going to be 1 plus root t dt. So this is saying we're going to be integrating with respect to t. Okay, well, in order to calculate out this definite integral, I'm going to need to use the fundamental theorem of calculus. Right, so let me go ahead and figure out what my antiderivative will be. My capital F of, actually I'll use t here, stay consistent. So something that has the derivative of 1, well, that's going to be t. and then something that has the derivative of root t. Well, remember root t, right, is the same thing as t to the 1/2. So if I was to follow my power rule for antiderivatives, right, this would be plus t to the 3/2, right? So I raise my power by 1, so from 1/2 or 0.5 to 3/2 or 1.5, and then I need to divide by my new exponent. So I need to divide by my new exponent 3/2. Okay, so this is what an antiderivative looks like. Now let's go ahead and evaluate this thing. So I'll kind of move over here. So we have 1/3, and this is going to be, f of, let's see, x minus f of x minus 3. Okay, plug that in. 1/3. So now everywhere I see a t, I'm going to plug in an x. So this is going to be x plus, and instead of dividing by this fraction here, let's multiply by the reciprocal. So again, instead of dividing by 3/2, I'm going to multiply by 2/3 and just kind of clean this up a little bit. And then this is going to be x to the 3/2, because again, everywhere I have a t, I'm going to be plugging in an x. Minus f of x minus 3. So I need to subtract away all of this. So it's a good idea to include parentheses here. So everywhere I see a t, I'm going to put an x minus 3. So x minus 3 instead of that first t. And then again, let me go ahead and write this as 2/3. So instead of dividing by 3/2, I'll multiply by the reciprocal. And then this is going to be x minus 3 raised to the 3/2. Not a lot of room there. Let's see if I can move things over a little bit. Nope. Let's go ahead and rewrite these parentheses then. Give me a little more room. Okay. There, that I'm happy with. So this is the 3-unit moving average of f of x. So this again is f bar of x. And that's it. That's all there is to it. It is a function. That's why it has the x's in it. It's not a number. That's the big difference between this one up here, the average or the mean. This one is a number, like 2, right? Versus the n-unit moving average is a function itself. That's why it has an x here. And that is the n-unit moving average actually is this green dotted line right here. It is a function in its own right. So it's going to have a variable, right? And so that's why we have x's, and that's kind of, you have to be okay with just leaving your answer as this. Okay, we can actually use this to find specific values, though. We can plug in values, so f bar or the moving average, so this is going to still be a 3-unit moving average, and then x is 4, right? So I can go ahead and plug in now x values just like in any other function. So I'll use your result in A. Plug in 4 everywhere you see an x. So this is going to be 4 plus 2/3 and 4 to the 3/2. Let me go ahead and just put that for right now. We'll evaluate this in a second. Minus, okay, and remember my parentheses, so 4 minus 3 would be 1 plus 2/3, and then 4 minus 3, that again would be 1 raised to the 3/2. Close a couple parentheses here. And so let's get out my calculator so I don't make any silly mistakes. And I'm going to take a line to just simplify the inside a little bit. So first of all, 4 to the 3/2. Let's pretend, we forgot how to do this. Well, we can plug it into our calculator. 4 raised to the 3/2. And the claim is this is going to be equal to 8. And the idea here is that when you have to raise something to the 1/2 power, 4 to the 1/2 power, that would be the square root. So if you took the square root of 4, you would get 2. And then if you cube that, right, because this really isn't the 1/2 power, it's the 3/2. So if I was to cube that, I would get 2 cubed, and that's how I knew it was going to be 8. Okay, so that's going to be 8. And let's go ahead and multiply this by 2/3. Let's add 4 to that. Kind of I'm working my way out almost, right? I have this part now, I added the 4, now I need to subtract away something. Okay, so I'm going to take that, and I'm going to subtract away something. Well, let's see. 1 to the 3/2. Well, 1 to any power is going to be itself. So I'm going to have 2/3 plus 1. So let me figure out what that is. So 2/3 plus 1. Okay, 1.666. And that's what I need to subtract away from my 9.333. So, okay. Let me go back a minute. I actually want my previous answer. I'll just type it in. 9.33333. And I'm going to subtract away 1.66666. Right? And so I get 7.66 repeating. So I still have the 1/3 out in front. I have 7.66 repeating. And so let's divide that by 3, or multiply by 1/3. Excuse me. There it is. 2.55 repeating. A little while. And there's my final answer. So this is the 3-unit moving average for f of x at x equals 4. Okay, and the claim is, of course, that moving averages are related to, actual averages. Let's go ahead and look at our answer in B and figure out what is this equivalent to? What average of f of x on what interval, right? So, okay, so our function is going to stay the same. It's going to be this 1 plus root x. And you can notice that I was on the interval then, right? If I'm plugging in 4 and I'm using a 3-unit moving average, then this would have been the integral from 4 minus 3 to 4. And again, this is a 3-unit moving average. So, and of course our function and stuff would have been here. And right, so this is the interval from, let's see, 1 to 4. And you can write 3 as, of course, 4 minus 1. So this is equivalent to the average of f of x over the interval from 1 to 4, right? That lines up with our previous definition here. 1 to 4, 4 minus 1, right? All lining up. So it is equivalent to the average of f of x over the interval 1 to 4. So, again, these moving averages are actually computing many average heights of a function. All right, last example here. If I invest $1,000 at 5% annual interest, compounded continuously, what is the average amount in your account over the first 2 years? Okay, so again, these are some more real-world statements, and they essentially come down to applying what we've been doing today, right? Because we want to know the average amount in our account over the first 2 years. So this is specifying the interval from 0 to 2. Okay, so we need a function, right? A function that's going to give out how much money we have, right? The amount in our account. Well, we know this, and we've written it down several times. So if compounded continuously, we know what these sorts of things look like. So we're going to have A equals our initial amount, so $1,000, times e to the rate. So it's not just 5, right? It's going to be 0.05. I have to convert this to a decimal. And then times t, however much time. So there is the amount in our account after t years. Okay. So I want to know the average amount in my account over the first 2 years. So therefore, I need to compute, again, our average. So this would be maybe a bar. And again, this is over 2 years. So I'm going to have 1 over 2 minus 0. So that's my b minus a, times the integral from 0 to 2 of our function. Right? So this is going to be 1,000 e to the 0.05 t dt. Okay. In order to speed things along, right, we could use the fundamental theorem of calculus, but let me go ahead and just use my calculator here. Okay? So let me calculate out this integral part. So math 9 gives me the fn int. All right, and I want to integrate 1,000 times e to the 0.05 Remember, the calculator likes x's, so we'll use x. All right, we want to integrate with respect to x on the interval from 0 to 2. Close parentheses, hit enter. $2,103. So we have still this part out here, times $2,103, and I should have written down the cents here. So let's say 40.42. Okay, so let's divide that by 2, or multiply by 1/2. And so the average amount in our account over those 2 years is going to be $1,051.71. 1,051.71. All right, and there we are. That's all there is to it. We'll see a few more examples in class. I'll see you then.